In 1783, British scientist John Michell sent a letter to the Royal Society. The letter proposed that a celestial body with the same density as the Sun, but a diameter over 500 times larger, would trap even its own light due to its immense gravity. The idea would later come to be known as a dark star. In 1915, Einstein introduced his general theory of relativity, explaining how massive objects can dramatically warp space-time. The following year, German physicist Karl Schwarzschild found a solution to Einstein's equations that described a point where gravity becomes infinite, a singularity. It was the first mathematical description of a black hole. A black hole's gravity is so extreme that it leads to a singularity at its core. Its overwhelming gravity swallows everything nearby, even light itself. A vast, dark hole that consumes what little light exists in the already black cosmos. That's a black hole. Or at least that's what scientists believed at the time. But in 1974, one scientist challenged this idea, British physicist Stephen Hawking. He argued that black holes don't just absorb everything, they actually emit light. Light coming from a black hole? How could that possibly be? Black holes have incredibly strong gravity, but it doesn't stretch infinitely far. There's a boundary beyond which nothing can escape. It's called the event horizon. Naturally, the event horizon lies in a vacuum. A vacuum might seem completely empty, but in reality it's not. According to quantum mechanics, even a vacuum teems with energy fluctuations, called quantum fluctuations. These fluctuations briefly borrow energy from space, creating pairs of particles and antiparticles. They appear for a fleeting moment, then annihilate each other, returning the energy as if nothing had ever happened. This process causes no problems, unless the pair forms right at the event horizon. In that case, one particle may fall into the black hole, while the other escapes, left without its partner. Since particles carry energy, to an outside observer, it appears as though the black hole is radiating energy, emitting light. This is why Hawking claimed that black holes aren't as dark as we once thought. It's what we now call Hawking radiation. But if a black hole radiates energy, the energy inside it must be decreasing, according to the law of conservation of energy. If this process continues steadily over time, the black hole's energy would gradually decrease, and eventually, it would have to disappear altogether. The discovery unsettled scientists and led to a troubling realization. Wait, what happens to everything inside the black hole? The matter it swallowed, and more importantly, the information those things carried. To this, Hawking responded, "The information that enters a black hole cannot be retrieved." He argued that when the black hole disappears, the information goes with it. This idea deeply confused scientists because it violated a fundamental principle of quantum mechanics, that information can neither be created nor destroyed. And yet, a black hole that absorbs information clearly still evaporates over time. This is what became known as the information paradox, a problem created by Hawking radiation. Some might wonder, what's the big deal if information disappears? But it is in fact a very serious problem. The information here isn't just data in the ordinary sense. It refers to quantum information. For example, hydrogen and oxygen combine to form water, and water boils at 100 degrees Celsius. Every material in the universe has its own unique physical characteristics, its quantum properties. Science has been built upon these fundamental traits. At its core, science is deterministic. It allows us to reconstruct the past, understand the present, and predict the future. All of this towering structure of science, is built on the belief that information is absolutely conserved. But black holes seem to erase that information. And if determinism breaks down inside a black hole, how can we be sure it won't break down elsewhere, even right before our eyes? That's the one scenario scientists are desperate to avoid. Fortunately, in 2004, Hawking retracted his earlier claim that information is lost. He proposed instead that information isn't lost, but either transformed into another state beyond our understanding, or sent into another universe or dimension, making it inaccessible to us. Many other hypotheses have been proposed along similar lines, because they preserve the law of information conservation and align, at least to some extent, with the determinism at the heart of quantum mechanics and science itself. Some might think, isn't that the same as being lost? But it's not. We live our lives accumulating countless experiences. It's no exaggeration to say those experiences shape who we are. Some once vivid memories fade over time. Some feel completely gone, as if they were swallowed by a black hole. And yet, those experiences, those memories, continue to affect our lives in many ways. They form invisible threads that link our past, present, and future. Just as we are part of this universe, so too are black holes. And that's why the information they contain can't truly disappear. It must persist in some form, because that invisible thread continues beyond the event horizon.